Between July 2024 and March 2025, astronomers tracked an object entering our solar system from an almost hyperbolic orbit. It was designated 3I Atlas, the third confirmed interstellar visitor after Oumuamua and Borisov. For months, the data looked ordinary until it wasn't. When 3I Atlas passed near Mars, instruments from NASA, ESA, and several university observatories recorded behavior that defied standard comet dynamics. Outgassing spikes, trajectory drift, spectral mismatches all layered inside one of the most complex observation campaigns in modern astronomy. So tonight, we piece together the complete timeline from the first signal to what Mars orbiters actually saw and what remains unspoken by the agencies. But before we go any further, make sure you're subscribed and comment "Avant" with where you're watching from and the exact time right now, because somewhere between your moment and Mars, the signal of 3I Atlas might still be traveling. Between July 2024 and March 2025, astronomers tracked an object entering our solar system from an almost hyperbolic orbit. It was designated 3I Atlas, the third confirmed interstellar visitor after Oumuamua and Borisov. For months, the data looked ordinary until it wasn't. When 3I Atlas passed near Mars, instruments from NASA, ESA, and several university observatories recorded behavior that defied standard comet dynamics. Outgassing spikes, trajectory drift, spectral mismatches all layered inside one of the most complex observation campaigns in modern astronomy. So tonight, we piece together the complete timeline from the first signal to what Mars orbiters actually saw and what remains unspoken by the agencies. But before we go any further, make sure you're subscribed and comment where you're watching from and the exact time right now, because somewhere between your moment and Mars, the signal of 3I Atlas might still be traveling. Silence in astronomy is never truly empty. It is filled with the faint hum of background radiation, the whisper of cosmic dust colliding in the dark, and the quiet ticking of instruments that have been listening for years. But the silence that surrounded 3I Atlas in its early months was different. It was the kind that carries expectation, the stillness before something is understood. When the object was first catalogued, it appeared as just another data point in the nightly feed from the Atlas telescope in Hawaii. A faint streak, moving faster than the near-Earth asteroids that usually populate those frames. The algorithms flagged it, and human eyes confirmed. The orbit didn't fit. It wasn't bound to the Sunday. That was the first clue, a trajectory so steep and clean that it could only belong to something passing through, not belonging here. At first, the scientific world reacted with calm curiosity. We had seen this before with Oumuamua in 2017 and 2I Borisov 2 years later, another traveller from the interstellar medium, bringing with it traces of the unknown. But this one was different in scale and timing. Its nucleus was estimated to be over 40 kilometers wide, perhaps the largest foreign object ever to cross our inner solar system. It wasn't just a visitor, it was a presence. For weeks, telescopes around the world followed it, measuring its light curve and rotational flicker. The numbers came in slowly, each update refining the shape of its orbit. Astronomers at JPL noticed something subtle, a delay between predicted positions and observed ones. The object wasn't where it should have been, not by much, but enough to make them look twice. They blamed it on calibration errors, solar pressure, or gas venting from the surface. Still, the pattern held. Meanwhile, the European Space Agency and NASA both prepared coordinated observation windows. There was quiet confidence at first. The data seemed stable, but when Atlas began to brighten earlier than expected, nearly half an astronomical unit sooner than any comet of its class, the silence deepened. No one wanted to speculate yet. Too many false alarms in the past had turned to noise. Then, something changed. Around late July, both ground and space-based instruments began reporting small but consistent outgassing spikes in the carbon dioxide band, far too active for a body still that far from the Sunday. The silence from official channels stretched longer. No press releases, no public briefings, just routine mission logs and archived observations. While the astronomical community whispered in private forums, it wasn't secrecy. It was caution, because science moves slowly, and nature often mimics the extraordinary before revealing itself as ordinary. But beneath that caution, a new question was taking shape. one that couldn't be answered by brightness curves or thermal models alone. Why was 3I Atlas behaving like this so far out? The Deep Space Network was instructed to begin passive tracking in early August. Using radar pings to refine the orbit, signals bounced off the object returned slightly weaker than expected, suggesting a surface that was unusually absorptive, perhaps rich in carbon or coated in dark dust. It wasn't reflective like ice. It absorbed light, and yet somehow radiated heat in uneven pulses. When plotted, those pulses created a faint rhythm, like a heartbeat barely visible through noise. Most dismissed it as telemetry interference. Others noted that the same pattern repeated 3 days later, picked up again by a different antenna. No one knew it yet, but that irregular echo, the small signature hidden inside the data, would later become one of the most debated anomalies in interstellar observation history. And so the silence before the data wasn't silence at all. It was the universe waiting, quietly, to be understood. It began, as many astronomical discoveries do, with a faint pixel that refused to behave. On the evening of the 12th of April 2024, a survey telescope atop Haleakala, the volcanic summit of Maui, swept its wide field across the pre-dawn sky. The Atlas System Asteroid Terrestrial Impact Last Alert System was performing its usual automated scans, designed to catch anything that might someday cross paths with Earth. But this time, the software flagged something unusual. A fast-moving streak, small yet bright, cutting diagonally across the frame. Its apparent motion didn't match any catalogued asteroid or comet. Within hours, cross-checks from the second Atlas telescope on Mauna Loa confirmed it. The object was moving far too quickly to be gravitationally bound to the Sunday. At first, the team thought it might be a miscalculation parallax confusion, perhaps a glitch in starfield alignment. But after the initial orbital fit was processed, one number stood out. Its eccentricity exceeded 1, meaning it wasn't looping around the Sun, it was merely passing through. Another interstellar object, only the third ever confirmed. The discovery message spread through the global network of observatories almost instantly. Within a day, telescopes in Chile, South Africa, and Spain were all pointed at the new arrival, logging coordinates and brightness variations. Early estimates suggested a nucleus diameter of 40 to 50 kilometers colossal when compared to Oumuamua, which was barely a fraction of a kilometer long. That size alone made 3I Atlas extraordinary. It wasn't a fragile shard of rock or a sliver of ice. It was a small world, a traveller carrying its own long story from beyond our Sunday. At Haleakala, the mood shifted from curiosity to quiet awe. The operators knew that every photon captured now would become part of an archive, studied for decades. They adjusted filters, testing for emission lines. Carbon dioxide appeared faintly. So did sodium. But the spectral readings were erratic, as if the object's surface wasn't uniform. Some portions gleamed with reflected sunlight, others swallowed it completely. Astronomer Dr. Eric Heinaut, consulting remotely from the European Southern Observatory, described it as a body that behaves like a comet, but shines like an asteroid. The dual nature was puzzling. Solid, metallic signatures in one scan, volatile gas release in another. It hinted that 3I Atlas might have been shaped in a far colder system, then hardened by radiation before being flung into interstellar space millions of years ago. For a brief window, Earth's telescopes captured it crossing the constellation of Serpens. The images showed a diffuse coma forming earlier than expected, an expanding envelope of dust and gas surrounding the nucleus. That shouldn't have happened yet. At nearly 3 astronomical units from the Sun, most comets remain dormant. Yet this one seemed awake. As news outlets caught wind of the finding, comparisons to Oumuamua flooded social media. But among scientists, the tone was more cautious. Oumuamua had been a mystery of shape and acceleration. 3I Atlas, however, was measurable, trackable, and massive enough to reveal its secrets if the data held. By late April, JPL had refined its orbit using radar data from Goldstone and confirmed what Atlas had hinted. The object's inbound velocity relative to the Sun was roughly 26 kilometers per second, arriving from a region near the constellation Lyra. In cosmic terms, that meant it could have originated anywhere between neighboring star systems, possibly ejected debris from a long-ruined planetary disk. The discovery at Haleakala didn't just add another entry to astronomy's logbook. It reawakened a quiet question buried since Oumuamua. What else is moving between the stars? How many fragments of other worlds drift unseen, slipping past our telescopes in silence? And perhaps most haunting of all, why do the few we do catch never behave the way physics predicts? At Haleakala, as dawn broke across the Pacific, the telescope dome began to close. The night's final exposure of 3I Atlas was stored and time-stamped its faint green coma, barely visible against the thin morning light. A silent beginning to what would soon become one of the most controversial space stories of the decade. From the moment 3I Atlas's orbital data was uploaded into the Minor Planet Center, something didn't add up. The early coordinates plotted a clean hyperbolic arc, consistent with an object just passing through our solar system. But over the following weeks, the path began to shift. Slightly, subtly, enough to make the mathematicians uneasy. A typical comet's motion can be modeled precisely using gravity, solar radiation, and predictable outgassing effects. But 3I Atlas refused to stay inside the equations. Its predicted trajectory and its observed path began to drift apart not by much at first, just a few thousand kilometers. Then, the deviation doubled, then tripled. At NASA's Jet Propulsion Laboratory, orbital analysts ran fresh simulations daily, feeding in data from optical observatories, radar reflections from Goldstone, and radio signals from ESA's New Norcia deep space antenna. Each update returned the same result. The object was accelerating in a direction that sunlight pressure alone couldn't explain. The vector was faintly sunward, not away the exact opposite of what's expected when radiation pushes on a comet's surface. Initially, the working theory was uneven outgassing. Perhaps one jet on the surface was venting more than the others, producing a small thrust. But even with that correction, the magnitude was wrong, nearly an order of magnitude greater than any measured before. By early May 2024, the anomaly had become undeniable. Dr. Davide Farnocchia at JPL's Center for Near-Earth Object Studies quietly updated the public database, tagging 3I Atlas with a non-gravitational parameter. It was the same phrase once attached to Oumuamua, the same clue that had split the scientific community into two camps 7 years earlier. To the cautious, it meant nothing exotic. Gas jets, unknown ices, solar torque. To others, it whispered something different, that perhaps 3I Atlas was not a typical comet at all, but a fragment of something larger, maybe even engineered. Still, science stayed patient. The acceleration data needed verification, so ESA's Gaia mission provided high-precision astrometry, tracking the object's micro-position shifts with milliarc-second accuracy. Gaia's measurements confirmed the trend. 3I Atlas was drifting sunward at a rate of roughly 0.0007 meters per second squared. Small, but persistent. Over months, that adds up to thousands of kilometers of unexplained movement. Meanwhile, the ExoMars Trace Gas Orbiter was instructed to keep a passive eye as Atlas approached Mars's orbital corridor. It wasn't officially part of its mission, but the data pipeline allowed it. When TGO's spectrometers picked up faint emission lines inconsistent with a simple dust coma, mission engineers quietly noted it. Something in the tail was ionizing differently, reacting to solar wind in asymmetric bursts. Across the Atlantic, the European Space Operations Centre, ASOC, in Darmstadt, plotted the growing divergence between prediction and observation. The team noticed that the anomalies seemed to align with specific solar wind conditions, spikes in magnetic field density, followed by minor orbital fluctuations. It was as if 3I Atlas were reacting not to light, but to space weather. Such coupling is rare. Comets don't usually care about magnetism. They follow gravity and thermodynamics. But if 3I Atlas carried metallic inclusions or charged particles trapped within its coma, magnetic interactions might produce microforces strong enough to alter its path. That was the leading hypothesis, one that balanced observation with physics, without leaping into science fiction. And yet, the numbers stayed strange. The direction of the acceleration occasionally flipped polarity, as if a hidden rhythm were at play. Goldstone's radar logs recorded micro-delays during these intervals. Not mechanical errors, but measurable changes in echo timing. By late June, researchers stopped calling it a deviation and began calling it the Atlas Drift, a trajectory that refused to behave, a motion that, even under scrutiny, seemed to rewrite its own script. As the object neared Mars, its unpredictable path forced mission planners to update their observation schedules daily. In astronomy, uncertainty is expected, but not like this. And when a celestial body begins to move against the models, it leaves scientists with only two options. Either the physics is incomplete, or something about the object itself is. Every comet that wanders into the warmth of the inner solar system eventually begins to breathe. Ice sublimates, gases escape, and sunlight paints the familiar glowing shroud we call a coma. But 3I Atlas began that transformation far too early. At a place where sunlight is little more than a whisper, more than 3 astronomical units from the Sun, a region where even the most volatile comets usually remain silent stones. The first hints came from the Neil Gehrels Swift Observatory. Its ultraviolet spectrometer detected faint spikes of carbon dioxide, the kind of emission one expects near 1.5 AU, not twice that distance. When the data reached the Atlas Discovery team, they ran the numbers again, convinced it had to be noise, but the signal held steady. The comet wasn't just outgassing, it was thriving in deep space. Within days, IRTF in Hawaii and the Very Large Telescope in Chile confirmed the anomaly. The coma was measurable, expanding at nearly 250 meters per second, with a density profile that implied continuous jetting from multiple regions across the surface. That suggested an active crust riddled with vents, yet no one could explain how such vents could function in temperatures hovering near 160 degrees Celsius. One hypothesis was supervolatiles, trapped carbon monoxide or molecular nitrogen, relic ices from the cold birthplaces beyond Neptune. Those ices can sublimate at lower temperatures, awakening a comet earlier, but even that theory faltered under the observed production rate. The coma was too dense, its brightness increasing by a factor of 10 within a few weeks. At ESA's Planetary Science Division, thermal models were recalculated using the latest data from Gaia and Mars Express. The surface would need to absorb and redistribute heat with an efficiency higher than any comet measured before. Something about its texture, maybe extremely low albedo dust or metallic inclusions, allowed it to trap warmth and vent it explosively from deep pockets. Meanwhile, amateur astronomers captured long-exposure images, showing a strange symmetry in the tail. Instead of the usual diffuse fan, it formed 2 thin filaments that occasionally bent against the solar wind. Spectroscopic readings hinted at charged dust grains, perhaps interacting with interplanetary magnetic fields. If true, the coma wasn't only made of gas, it carried electric memory, dust particles charged enough to dance with magnetism. By late July, NASA's Infrared Telescope facility detected periodic flickers in the infrared bands, repeating every 6 hours. That rhythm matched a slow rotation, suggesting that the jets pulsed as 3I Atlas turned, like geysers briefly facing the sun before fading back into shadow. The picture that emerged was of a fractured, tumbling body, wrapped in its own halo of vapor, shedding pieces of itself into the void. But even that story had complications. Observers using JWST's NIRSpec instrument found traces of compounds rarely seen in comets, complex organics, perhaps tholins or carbon chains and unusually strong silicate features, more akin to asteroidal dust. 3I Atlas seemed to blur the line between icy wanderer and rocky fragment. Its coma glowed emerald green in color-corrected imagery, the telltale sign of diatomic carbon reacting to ultraviolet light. Yet deeper layers emitted dull reddish hues, almost as if the object contained 2 separate chemistries. The strangeness prompted a quiet joint session between ESA and NASA specialists. No one publicly said it, but the conversation circled a single unsettling thought. Maybe 3I Atlas wasn't behaving like a comet because it wasn't born like one. Perhaps it was once part of a differentiated planetesimal, its volatile core sealed under rock until an ancient impact set it adrift between stars. Whatever the origin, the coma shouldn't have existed where it did. It was a living contradiction, a cold body that acted warm, a distant traveller already wrapped in light before entering the sun's true domain, and as it crept closer to Mars, that impossible glow only grew brighter, refusing to fade, daring the universe to explain it. In early August 2024, the European Space Agency prepared what was supposed to be a routine update, a set of calibrated photometric frames from Gaia, Mars Express, and several ground-linked stations had been scheduled for public release through ESA's data portal. Nothing extraordinary, just another step in the transparent cataloguing of the new interstellar visitor. But what followed was anything but ordinary. At 9 CET, the files went live, a compressed archive containing high-resolution images and brightness curves of 3I Atlas, covering a 2-week period as it crossed 2.2 astronomical units from the Sunday. Within hours, astronomers began to notice something odd buried inside the data. One subset of images taken by Gaia's BP divided by RP spectrophotometers displayed a sudden flare, a sharp increase in brightness that lasted less than 4 minutes before fading back to baseline. The timing of the flare corresponded precisely with a period when Mars Express happened to have the object within its wide-angle imager field. At first, no one paid much attention. Flares happen. Cosmic rays strike sensors. Calibration errors slip through. But the anomaly didn't behave like noise. It wasn't random. The light curve showed a smooth rise, a defined peak, and a symmetric decay, a pattern consistent with an emission event, not a sensor glitch. By evening, a handful of researchers from the Paris Observatory and the Max Planck Institute for Solar System Research had downloaded the data and started cross-matching timestamps. When they overlaid the Gaia and Mars Express readings, the alignment was exact to within a tenth of a second. 2 independent spacecraft, hundreds of millions of kilometers apart, had recorded the same 4-minute burst. Then, quietly, the data vanished. At 23:47 CET, the archive link on ESA's open access server returned a 404 file not found. The original press notice was replaced with a short revision, citing a processing inconsistency and promising a corrected dataset soon. The corrected version arrived 2 days later, smaller, cleaner, and missing the keyframes. The 4-minute window was gone. Officially, ESA's statement was simple. The preliminary release contained calibration artifacts related to sensor drift. The dataset has been updated accordingly. But the explanation didn't satisfy those who had seen the original files. Calibration drift doesn't produce identical anomalies across independent instruments separated by millions of kilometers. Inside ESA's European Space Operations Center, ESOC, internal emails later leaked through anonymous sources confirmed that the decision to retract was deliberate. The flare had triggered unexpected questions from partner agencies. Some suspected it was a reflected solar event, perhaps sunlight glancing off a tumbling surface of unusually high albedo. Others argued it might have been a jet, a powerful outgassing spike releasing trapped CO2 or carbon monoxide. But the energy profile didn't fit either scenario. The intensity of the burst, when converted from magnitude to absolute luminosity, implied an output far greater than any known cometary vent could produce, equivalent to several gigawatts of radiant energy in visible wavelengths. It was, quite simply, too bright for a natural jet and too short for a sustained reflection. In the days that followed, discussion threads appeared across private astronomy networks. Observers from the Canary Islands and La Silla Observatory noted that their own long-exposure images taken around the same time showed a faint bloom, an expanding halo not visible the night before. Yet none of these images were mentioned in ESA's reissued documentation. Official silence settled in. When asked at a September press briefing, a communications officer for the Gaia mission deflected. "We continually review early release data for consistency. Our goal is reliability over speed. For the public, the moment passed. But for those watching closely, ESA's quiet release marked a turning point. It wasn't proof of anything extraordinary, just a gap in the record, a shadow where data should have been. Still, in science, absence can be as telling as presence. Whatever 3I Atlas had done near Mars in early August, it was bright enough for 2 spacecraft to notice, and unsettling enough for one agency to quietly erase. By late October 2024, 3I Atlas had crossed into the orbital corridor of Mars. For months, its path had been tracked with almost obsessive precision, but as the object drew closer to the red planet, even the best models began to lose confidence. The non-gravitational acceleration that had puzzled researchers earlier in the year continued to fluctuate, sometimes growing stronger, sometimes vanishing entirely, as if the object itself were reacting to something in the environment rather than obeying a fixed mechanical law. The European Space Agency's ExoMars Trace Gas Orbiter, TGO, became the first deep space asset to witness the event up close. While its main mission is to analyze methane and other atmospheric gases, TGO's high-resolution camera and ultraviolet spectrometer were repurposed to observe the incoming visitor. On November 17, the first images arrived. A dim point wrapped in a faint greenish haze trailing a narrow, twisting tail. The readings confirmed what ground telescopes had hinted for weeks. 3I Atlas was alive with activity. At the same time, NASA's MAVEN spacecraft prepared its own observation sequence. Its magnetometer, particle detectors, and solar wind analyzers were already tuned to monitor the Martian ionosphere. On the night of November 29, they registered something never seen before. A surge of magnetic flux lines rising from the dayside ionosphere, curving outward and then connecting, almost like invisible threads, toward the direction of the incoming object. For 12 hours, the Martian magnetic field behaved as if being gently pulled. The flux ropes, thin filaments of plasma, stretched tens of thousands of kilometers above the planet. To mission scientists, it looked like a temporary magnetic bridge forming between Mars and 3I Atlas's coma. No known mechanism fully explained it. The next morning, the Mars Color Imager on board Mars Reconnaissance Orbiter captured a subtle, diffuse brightening in the upper atmosphere. A pulse of reflected sunlight from aerosols suddenly illuminated. It lasted less than an hour. MAVEN's instruments confirmed a simultaneous spike in charged particles and ultraviolet radiation. Something had disturbed the calm equilibrium of the Martian sky. Speculation spread quietly through the research channels. The most conservative explanation suggested that fine, ionized dust from 3I Atlas's tail had been swept into Mars's magnetosphere, triggering temporary electric coupling. If so, it would be the first recorded instance of an interplanetary body measurably influencing another planet's magnetic environment. Yet others weren't convinced. Some of the readings indicated phase-lock timing between fluctuations in the comet's own magnetic signature and the Martian response, as if the two were resonating. That kind of synchrony would imply active electromagnetic feedback, the kind seen in artificial systems or in binary plasma interactions. Still, no one dared to publish that theory openly. Back on Earth, telescopes from the European Southern Observatory and ALMA detected complex radio structures in the coma. The signal varied in amplitude at regular intervals, producing harmonics similar to those found in auroral emissions. It was possible that Mars's induced magnetosphere was echoing the comet's charged tail, the way Earth's poles sometimes sing in response to solar storms. By early December, 3I Atlas had passed within 0.09 astronomical units of Mars, close enough that even the planet's thin gravity well began to tug at its tail. A faint dust streamer detached and curved toward the planet, dissipating in the solar wind. No impacts, no collisions, just a silent brush, a cosmic handshake that left both bodies changed in subtle ways. When the encounter ended, Mars's atmosphere took nearly 2 sols to return to normal electrical conditions. MAVEN's instruments recorded lingering plasma waves, slowly decaying into background noise. For planetary scientists, it was a reminder of how fragile and interconnected the solar system really is. In press releases, both ESA and NASA described the event in cautious language, a temporary magnetic disturbance associated with cometary passage. But among those who had watched the data in real time, it felt like more than that. It was as if Mars itself had momentarily awakened, answering a visitor's call before silence reclaimed the sky. 12 hours after the strange magnetic filaments faded from MAVEN's readings, Mars exhaled. It wasn't visible to the naked eye, nor to the orbiter's invisible wavelengths. But in the ultraviolet and X-ray spectrum, something rippled through the thin Martian sky, a sudden, synchronized shimmer that lit the ionosphere like a heartbeat. The event lasted less than 15 minutes. It began as a sharp spike in ultraviolet flux detected by the Imaging Ultraviolet Spectrograph, IUVS, aboard NASA's MAVEN orbiter, centered above the planet's dawn terminator. The reading climbed by nearly 30% before dropping back to baseline, followed by a cascade of smaller oscillations. At the same moment, ESA's trace gas orbiter registered a brief surge in ion density at roughly 120 kilometers altitude. Two spacecraft, thousands of kilometers apart, seeing the same pulse at the same time. Planetary scientists first suspected a routine cause: solar flare activity. But when teams checked data from the Solar and Heliospheric Observatory and the GOES space weather satellites, the solar wind was quiet, No flare, no coronal mass ejection, no geomagnetic shockwave travelling through the inner solar system. Mars had pulsed on its own. For days, researchers combed through telemetry, aligning timestamps from different missions. MAVEN's particle detectors had caught something subtle, a faint, wave-like modulation in the incoming electron flux, as if a train of energy had passed through the Martian magnetotail. The shape of the wave matched a low-frequency oscillation known as an Alpha-Ven wave, typically generated by magnetic disturbances in plasma. But there was no storm, no interplanetary trigger. The only moving body nearby was 3I Atlas. At that time, the interstellar object was receding from Mars's orbit, its glowing coma stretched into a long arc by the solar wind. Spectrographic analysis from ALMA indicated sporadic bursts of ionized CO2, leaving the coma in coherent jets, not random outgassing, but structured emission, pulsing in rhythm with the very frequency MAVEN had observed. The match was eerie. No one wanted to jump to conclusions, but the correlation was undeniable. Every time 3I Atlas emitted a spike of ionized gas, Mars's upper atmosphere reacted roughly 40 minutes later the time it would take a plasma wave to travel across the intervening distance. The data looked almost like communication, though no one dared to use that word in print. Inside ESA's Planetary Aeronomy division in Nordwijk, a joint analysis was conducted. The conclusion was conservative yet profound. Energy transfer between cometary plasma tail and Martian ionosphere cannot be excluded. In simpler terms, something from 3I Atlas had reached Mars. During that same week, faint auroral glows were detected on the planet's night side, stretching across mid-latitudes where auroras rarely appear. The phenomenon was too short-lived for imaging, but MAVEN's detectors caught the spectral signature of atomic oxygen excitation, the same mechanism that paints Earth's skies green. On Mars, however, the light was invisible to the human eye, a ghostly flash in wavelengths our retinas can't perceive. As the pulse faded, one final anomaly appeared. Mars's neutral gas and ion mass spectrometer, NGIMS, picked up trace increases in isotopic oxygen and nitrogen atoms freshly energized, drifting into higher altitudes. The atmosphere had literally expanded, if only slightly, responding to a transient wave of energy that no one could yet explain. For planetary scientists, it was both exhilarating and unsettling. Mars was supposed to be silent, passive, predictable. Yet during those 15 minutes, it acted alive like a resonant drum briefly struck by a cosmic hand. When the data reached the press offices, both NASA and ESA released identical phrasing: transient ionospheric fluctuations consistent with external plasma interaction. The words were careful, antiseptic, and almost meaningless to the general public, but those who had seen the real graphs, the synchronized spikes, the harmonics aligning perfectly with 3I Atlas's own emission cycles, understood the weight of what had happened. For the first time in recorded history, Mars had pulsed in time with something not of this solar system. And though the atmosphere returned to calm within minutes, the memory of that heartbeat lingered, a silent reminder that even in the void between worlds, forces can still find resonance. When scientists reviewed MAVEN's magnetometer data from late November 2024, the lines on the plot looked like an artist's sketch, looping, twisting filaments stretching outward from Mars into space. For hours, the planet's weak magnetic field, usually a chaotic scatter of localized crustal regions, had reconfigured into long, coherent strands. They reached far beyond the expected boundaries of Mars's ionosphere, forming arcs that extended tens of thousands of kilometers toward the incoming 3I Atlas. No one believed it at first. Mars doesn't have a global magnetic field like Earth. Its magnetism is patchy, fossilized in the crust, unable to sustain large-scale connections. Yet, for a full half day, the data suggested otherwise. The planet appeared to weave magnetic threads into space threads that seemed to reach toward the same direction as the comet's tail. MAVEN's principal investigator, Dr. Shannon Curry, described it in simple terms. It looks like the planet reached out, but what triggered it was unclear. The solar wind at that time was calm, with no coronal mass ejections or shocks to explain such coherence. Something else had ordered the chaos. The European Space Agency's Mars Express, operating in a higher orbit, recorded complementary evidence. Its magnetometer detected faint ripples in the local field strength, oscillating at nearly the same frequency as variations measured within 3 I-Atlas's plasma tail by ground-based radio telescopes. The phase alignment between the two sets of data separated by over 60 million kilometers was startling. Statistically, the odds of coincidence were near zero. At ESA's European Space Operations Centre, ESOC, in Darmstadt, analysts superimposed the curves. The rise and fall of magnetic intensity around Mars mirrored the modulation of radio emissions from 3 I-Atlas, with a delay consistent with interplanetary propagation time. In other words, the two systems seemed to be responding to one another not by direct force, but through the medium of the solar wind itself. This phenomenon wasn't entirely new in physics. Plasma can carry magnetic structures over vast distances. When a charged object such as a comet releases streams of ionized gas, those particles can interact with solar wind magnetic fields, creating flux ropes. If those flux ropes encounter another magnetic region, they can reconnect, forming temporary bridges of plasma and magnetism. But such events have only ever been observed between the Sun and planets, not between two moving bodies. What MAVEN detected was the first recorded interplanetary magnetic connection between a planet and a transient object, a literal thread between worlds. For hours, electrons and ions flowed along these invisible highways. MAVEN's particle detectors measured sudden enrichments of high-energy protons that didn't match solar wind profiles. Some of them carried directional signatures pointing from the region of 3 I-Atlas rather than from the Sunday. Though faint, the implication was stunning. Energy, or at least charged matter, was travelling along that bridge. In the following days, the Mars Advanced Radar for Subsurface and Ionospheric Sounding, MARSIS, aboard Mars Express noticed residual disturbances. Reflected radar pings returned slightly delayed, as if the ionosphere's upper boundary had been temporarily stretched upward. The data fit perfectly with a scenario where the planet's magnetic topology had briefly expanded, pulled outward like taffy. Under an unseen tension, the ESA and NASA science teams released a joint technical note, acknowledging a transient magnetic coupling event of uncertain origin. Behind closed doors, the word coupling was debated. It suggested a level of synchronization that many found uncomfortable. How could an interstellar object, with no awareness and no control, generate a structured magnetic connection with a planet? A few researchers offered a daring explanation. They proposed that 3 I-Atlas carried a residual magnetic moment of its own, perhaps the remnant of a once active metallic core, long frozen yet still faintly magnetized. As it passed through the solar wind, that magnetic field could have resonated with Mars's scattered crustal fields, aligning them temporarily. In essence, Mars might have recognized a familiar tune in the cosmic static. When the alignment broke, the filaments collapsed quietly. The data flattened back into noise. But for those 12 hours, Mars and 3 I-Atlas had shared a conversation written in magnetism, a silent exchange across millions of kilometers, invisible to the eye yet unmistakable in the instruments. The magnetic threads between worlds didn't last long, but their existence proved something profound. Even across the emptiness of space, two distant bodies could, for a fleeting moment, share the same field, two worlds connected not by gravity, but by the whispering architecture of invisible lines. Telemetry doesn't simply vanish. Every spacecraft, from the smallest CubeSat to the largest planetary orbiter, maintains redundant systems precisely to prevent it. Yet, during the week following 3 I-Atlas's closest approach to Mars, data streams from multiple missions thinned, stuttered, and in some cases, disappeared altogether. It began quietly on the 3rd of December 2024, when engineers at the European Space Operations Centre, ESOC, in Darmstadt, noticed a sudden loss of contact with the ExoMars trace gas orbiter. The outage lasted just under 7 minutes, brief enough to avoid headlines, but long enough to leave an unexplained gap in its atmospheric log. When connection was re-established, the spacecraft's instruments reported nominal conditions. The only oddity was a short burst of corrupted packets, garbled in the deep space downlink as if something had scrambled the signal mid-transmission. Hours later, a similar hiccup appeared in NASA's MAVEN telemetry feed. The orbiter entered safe mode unexpectedly, triggered by a transient power surge in its communications array. The onboard system recorded no solar flare, no cosmic ray spike, no hardware fault, just an unexplained electromagnetic spike lasting 0.4 seconds. Mission Control restored full function within the hour, but an entire sequence of magnetometer and plasma wave readings from that period was lost. When engineers compared the two incidents, they realized the gaps overlapped precisely the same moment, separated by a fraction of a second. Two orbiters, run by different agencies, on different networks, had gone partially dark at the same time. Officially, both teams filed it under coincidental transient, but those inside ESOC's telemetry department weren't so quick to dismiss it. A third event, this time from Mars Express, added weight to the mystery. Its subsurface radar instrument, MARSIS, reported a sudden loss of carrier lock, followed by a reboot that erased its internal timestamp counter. For 4 hours, the radar operated without synchronizing to ground clocks, rendering its data practically useless. Behind the scenes, engineers reconstructed partial data from auxiliary subsystems. In doing so, they noticed something subtle. The missing minutes aligned with a measurable increase in background radio noise across X-band frequencies. The static wasn't random. It pulsed, faintly modulated, with a frequency that matched emissions observed days earlier from 3I Atlas's coma. In the control rooms, that realization landed like a quiet shock. The object was already moving away from Mars, receding fast along its outbound path, yet its signature still resonated across the Martian sky. Could its plasma tail have interfered with orbiters' transmissions? Theoretically, yes, but the geometry didn't fit. The object was no longer aligned with the direct line of sight between the spacecraft and Earth. To jam both simultaneously, it would have needed to emit across a vast arc of space, something far beyond any natural phenomenon known. Within a week, the public archives updated with data unavailability notices. The missing blocks were excised from online repositories, leaving smooth, uninterrupted records as if those minutes had never existed. Only in the internal mission logs did the timestamps remain blank, silent placeholders marking a moment that instruments could not explain. At a December coordination meeting between ESA and NASA, the term telemetry blackout was avoided. Instead, the official phrase became interference during deep space relay. It sounded harmless, procedural, but the scientists knew better. Telemetry is the heartbeat of spacecraft. When it falters, it means something has touched the signal. Speculative papers soon circulated privately. One argued that a dense plasma wave from 3I Atlas's tail might have refracted the communication beams, bending radio paths through an invisible curtain of charged dust. Another suggested a localized electromagnetic pulse, perhaps from solar wind compression, had temporarily overwhelmed receivers. Yet no solar event matched the timing, and the energy needed for such interference remained implausibly high. In the end, the official reports listed cause undetermined. But among the engineers who'd watched their screens flicker, a quieter story endured. For 7 minutes on that December morning, the machines orbiting Mars went deaf, as if the planet itself had fallen under a veil. When contact returned, the sky was calm again. No damage, no warning, just silence where data should have been. And in the vast archive of spaceflight telemetry, that silence remains the most eloquent line of all. Cometary dust has always been a faithful storyteller. It reveals composition, rotation, and even the thermal past of a wandering body. When sunlight strikes, the smallest grains scatter outward, creating the familiar luminous tails that trace across the heavens. It is predictable physics, the kind that comforts astronomers because it never surprises. But 3I Atlas refused to play by those rules. As the interstellar object passed beyond Mars's orbit, researchers from the European Southern Observatory, ESO, and ALMA expected its dust plume to disperse naturally under the pressure of solar radiation. Instead, high-resolution imaging in mid-December 2024 showed something no model could reproduce. The dust was holding its shape. Rather than drifting outward into the solar wind, the coma's particulate halo seemed to stabilize a faint filamented structure wrapped tightly around the nucleus, rotating in sync with the body itself. The pattern resembled a magnetic cage, its outer layers rippling but never scattering. The light curve confirmed this. Brightness variations repeated in 6-hour intervals, perfectly consistent with rotational modulation. If radiation pressure were dominating, the tail would have elongated asymmetrically, yet it stayed short and compact, like a sheath of particles locked in orbit. Initial theories proposed cohesive dust clumping due to electrostatic charging, the kind that sometimes happens on airless bodies when ultraviolet light knocks electrons off the surface. But even that couldn't explain the coherence over such vast scales. Dust cohesion occurs over meters, not thousands of kilometers. Then came the polarimetric data from the VLT's FORS-2 instrument. It revealed an unexpected alignment of dust grains. Their reflected light was polarized in a single orientation, indicating that the particles were spinning together, almost as if choreographed. Magnetic alignment was the only plausible cause. If the dust contained metallic or ferromagnetic material, nickel, iron, or magnetite, the surrounding plasma environment could have locked them into a stable configuration, tethered by a faint magnetic field extending from the nucleus. But that idea carried an implication no one wanted to say aloud. 3I Atlas would have to possess a magnetic field of its own. The data from Goldstone's radar lent quiet support. Radar echoes scattered off the object, displayed polarization flips that alternated predictably, a phenomenon usually seen in metallic asteroids rather than icy comets. The echoes hinted at a dense, perhaps partially conductive crust, a surface capable of storing charge or interacting with solar magnetic fields in complex ways. When scientists modeled the behavior using plasma simulation software at ESA's Space Weather Laboratory, the results were stunning. The dust surrounding 3I Atlas could indeed form a stable toroidal field, a ring-like halo maintained by rotating charge differentials. As the body spun, it might have generated weak but coherent magneto-hydrodynamic currents, corralling the dust into a confined envelope. In essence, the object behaved like a natural dynamo, briefly alive with electromagnetic order. The implications stretched beyond comet science. If 3I Atlas carried remnant magnetism from its parent system, the frozen memory of an ancient planetary core, it could explain both its anomalous trajectory and its resistant dust sheath. The solar wind wouldn't simply push it, it would interact with it, twisting around it the way air flows over the wings of an aircraft. Still, not all agreed. Some argued that instrumental errors or viewing angles had exaggerated the effect. Others pointed out that without in situ measurements, the so-called static dust field might just be a visual artifact overlapping tails aligned with the solar wind rather than against it. But the pattern persisted. Even weeks later, when 3I Atlas moved farther from Mars, its halo refused to fade. The dust neither diffused nor scattered as expected. It shimmered faintly in reflected sunlight, still hugging the body as though bound by invisible tension. In the quiet halls of observatories, astronomers compared frames taken weeks apart, watching the same filaments twist and return, again and again. Someone nicknamed it the ring that breathes, dust that didn't drift, particles that wouldn't let go, a silent, stubborn cloud clinging to a visitor from another star holding its shape long after physics said it shouldn't. Every celestial object tells its story in light. When a telescope disperses that light into a spectrum, each dip and spike, each wavelength absorbed or emitted becomes a fingerprint of chemistry. From those fingerprints, astronomers can read what a body is made of, what temperature it keeps, even how it moves. But when scientists compared the light signatures of 3I Atlas from different observatories, the fingerprints didn't match. They contradicted each other, as if the object were showing a different face to every lens. It started in mid-December 2024. Shortly after the Martian encounter, ESA's Gaia mission captured a clean, visible light spectrum as the comet brightened in the early morning sky. The data suggested a classic carbon-rich profile, broad absorption bands from diatomic carbon and CN radicals, typical of cold, volatile comets. Nothing remarkable. Yet days later, NASA's Infrared Telescope Facility, IRTF, in Hawaii, recorded something entirely different. In the infrared, the ratios of silicate to carbon features were inverted. Instead of ice dominating, it looked metallic, reflective, even dry. Two telescopes, two completely incompatible stories. When cross-comparisons began, a third contradiction appeared. ALMA, operating in the millimeter band, detected emissions from sulfur-bearing molecules, SO2 and H2S, at concentrations nearly impossible for a body of interstellar origin. Those gases usually form in planetary atmospheres or volcanically active regions, not in the frozen interstellar dark. Either the comet was releasing complex gases it couldn't possibly contain, or the readings were being distorted by something in the coma. the deeper the analysis went, the stranger it became. Using spectroscopy from JWST's NIRSpec instrument, researchers expected to confirm the IRTF's metallic hints. Instead, JWST showed volatile organics, ethane, methanol, and formaldehyde. The ratios didn't even come close to matching the infrared or visible results. At one wavelength, Atlas appeared to be an ice-covered wanderer. At another, a baked fragment of rock. These inconsistencies were too large to blame on calibration. So, the European Southern Observatory team began modelling the object as heterogeneous a body composed of multiple materials exposed by rotational cycles. But even that didn't fit cleanly. To create the observed ratio swings, 3I Atlas would have to rotate in such a way that one hemisphere was almost entirely metallic and the other entirely volatile, an unlikely configuration for any natural object. Some of the brightest minds in cometary physics proposed a subtler idea. Perhaps 3I Atlas's coma wasn't transparent. If its surrounding plasma contained charged particles or magnetized dust, it could polarize and scatter incoming light unevenly, making different wavelengths appear stronger or weaker depending on viewing geometry. In other words, the object wasn't changing the space around, it was bending the truth. To test that, ESA's Bepi-Colombo spacecraft, then cruising near Mercury, was enlisted for a rare side experiment. Using its plasma wave receiver, it listened for distant radio harmonics reflected from 3I Atlas's plasma tail. The signal was faint, but structured a complex oscillation that corresponded to varying ion densities. When mapped to the optical data, those oscillations lined up with the moments of spectral disagreement. The conflict wasn't in the rock or ice. It was in the ionized envelope surrounding it, distorting how light left the comet. Even so, that discovery raised deeper questions. For the plasma to warp spectra so dramatically, it would need to be unusually dense and magnetically organized, capable of redirecting specific wavelengths. Natural comets produce turbulence, not order. Something about 3I Atlas's electromagnetic environment was too clean, too consistent, as if tuned. Officially, scientific journals published cautious language: anomalous spectral variability, likely caused by complex coma dynamics. But within closed workshops, researchers admitted they had never seen a body display such conflicting spectral ratios over so short a time. One ESA analyst described it best: "It's like trying to analyze sunlight through stained glass, but the colors keep rearranging themselves." In the end, no single explanation survived peer review. Every wavelength told a different version of the truth, and somewhere between those contradictions, 3I Atlas continued on its path, a shifting mirror in the void, defying every spectrum that tried to define it. Radar never lies. When all else fails, when light bends, when spectra contradict, when telescopes see too much or too little, radar gives the universe a simple question and waits for an echo. That's what the Goldstone Deep Space Communications Complex in California was built to do: to listen, with patience, to the silence between the stars. And for a time, it did. Through the summer and autumn of 2024, Goldstone's 70-meter antenna pulsed gentle streams of microwaves toward 3I Atlas, measuring each return with millisecond precision. The first echoes came back weak but consistent, confirming the size estimates made at Haleakala, a nucleus roughly 40 kilometers across. Irregular, perhaps double-lobed. The reflections hinted at a surface surprisingly smooth for a comet, with radar albedo values more akin to metallic asteroids. It was puzzling, but still within the boundaries of nature. Then, just after December 19, as 3I Atlas approached the midpoint between Mars and Earth, the echoes began to change. The signal-to-noise ratio dropped sharply. Instead of clean, narrow peaks, the returns fractured into faint, stuttering bursts. At first, operators suspected atmospheric interference. Winter storms over the Mojave were notorious for disrupting microwave links. But secondary dishes in Spain and Australia, both part of the Deep Space Network, showed the same distortion. The object's radar signature was fading. By December 22, Goldstone transmitted another sequence, a series of coded pulses meant to refine surface scattering models. Nothing came back. Not noise, not echo, not even the usual background hiss. It was as if the signal had been swallowed whole. Technically, radar silence is impossible. even if the beam misses its target. Stray reflections from dust or plasma normally bounce home. Yet for 36 hours, Goldstone's detectors recorded zero coherent return. Engineers recalibrated, retuned, and retried, using lower frequencies and alternate polarization angles. Still nothing. The sky had gone deaf. Inside the control room, the mood shifted from confusion to unease. The same system had pinged Mars's moons the night before without issue. The transmitter worked flawlessly. The receivers were clean. Only when pointed at 3I Atlas did the silence appear. The European Space Agency's Sobreros station attempted a cross-check. Its smaller dish caught a whisper of something, a broad, diffuse echo, delayed by nearly 3 seconds more than predicted. The amplitude was so low it bordered on the detection threshold, but the timing implied the reflection was not from the comet's nucleus, but from material behind it, possibly a plasma sheath or detached fragment. Goldstone repeated the observation at dawn, and again that evening. Both times, the delay persisted, as though the radar pulse was slipping through a curtain of ionized gas before returning. The following day, an internal memo circulated among the Deep Space Network engineers. The language was dry, but the message unmistakable. Radar returns from 3I Atlas have ceased to be coherent. Object presently non-reflective at X and S bands. Investigation ongoing. Unofficially, some began calling it the blackout. In the press briefings that followed, NASA offered a simpler explanation. The radar beam likely dispersed as the object's coma thickened, scattering the signal into noise. It was plausible comets do grow opaque at close range. But the timing bothered many. The blackout had begun just as optical telescopes reported the dust halo shrinking, not thickening. A few independent researchers suggested something more subtle. If 3I Atlas possessed a magnetized envelope as earlier data hinted, then incoming radar waves might have been absorbed through electron-cyclotron resonance, effectively trapping the signal instead of reflecting it. In other words, Goldstone hadn't stopped transmitting. Space itself had stopped answering. For 2 weeks, the observatory kept trying, logging every failed attempt. The silence held firm until early January, when a faint, flickering echo reappeared, weak, distorted, and shifted in frequency, as though bouncing off a moving shell rather than a solid core. No official report ever named the cause. The data remains buried in technical appendices, labeled insufficient return. Nasida's fable, but for those who were there, sitting in the darkened room as the world's largest ear strained for a whisper that never came, the memory endures. A machine built to listen across the solar system had spoken, and for the first time in decades, the universe had refused to speak back. Every comet has a moment of truth, a window before perihelion, when the distance to the sun shrinks enough to melt secrets long frozen in the dark. For most, that moment is bright and predictable. Outgassing intensifies, the coma expands, and sunlight unravels the chemistry of the nucleus for all to see. But as 3I Atlas curved inward toward its closest solar approach in early February 2025, astronomers faced something altogether stranger. This was supposed to be the phase when the object revealed its true nature. After months of conflicting data, metallic echoes, organic vapors, plasma alignments, the heat of the sun would strip away ambiguity. Instead, it stripped away visibility. On January 26, just 10 days before perihelion, the Solar and Heliospheric Observatory first caught the incoming interstellar traveler on its wide-field coronagraph. The images were faint but clear, a compact nucleus trailed by a narrow emerald green tail. Over the next 48 hours, the tail thickened, the nucleus brightened, and then, inexplicably, the light began to fade. At first, astronomers assumed a fragmentation event, that the body was disintegrating under solar pressure. Yet, spectra from ESA's solar orbiter contradicted that idea. Instead of increasing dust and gas, emission lines weakened. The object seemed to absorb more light than it reflected, as though developing a dark skin against the sun's glare. Across the Deep Space Network, radar teams prepared to resume contact. Goldstone, still recovering from the December blackout, scheduled its next attempt for February 3, the night before the object reached its minimum distance of 0.48 astronomical units. The transmissions went out as planned. No echo returned. Then came the quiet that would define the event. For nearly 72 hours, Every major observatory from Hubble's Wide Field Camera 3 to JWST's NIRCam reported severe tracking inconsistencies. 3. iAtlas's position no longer matched its predicted coordinates. It was drifting again, but this time, the deviation wasn't lateral. It was radial inward. The object seemed to be falling faster than gravity alone would allow, as though something ahead of it was drawing it in. By February 4, the glow vanished completely from SOHO's sensors. For a full 20 hours, the region around its trajectory was blank, a gap in sunlight, where a comet should have been burning at maximum brightness. Astronomers called it a visibility minimum, a polite phrase for something they could not explain. When the object reappeared late on February 5, its signature was different. The tail was gone. The coma, once carbon-rich and luminous, had contracted into a thin, asymmetric plume. Instead of brightening after perihelion, as comets do when they retreat from solar heat, 3 iAtlas continued to darken. Its absolute magnitude dropped by nearly 2 orders, as if the object had consumed its own reflection. ESA's internal brief summarized the event with unsettling brevity: transient obscuration during perihelion passage, possible surface phase change. But outside the technical phrasing, a deeper anxiety crept in. Observers noted that during the blackout, solar wind data from Parker Solar Probe registered a tiny but measurable deflection, a kink in particle flow that rippled outward like a shadow passing across the sun's face. Whether coincidence or correlation, the anomaly lined up perfectly with the hours when 3 iAtlas was invisible. In the weeks that followed, the scientific community treated the episode with the same careful silence they had shown since discovery. Theories ranged from surface polymerization, where heat fuses volatile molecules into a carbon black shell, to plasma shielding caused by magnetic interference. Others whispered of artificiality, though always off record, in hushed tones after conferences. Whatever the cause, the window before perihelion gave astronomers something rarer than data. It gave them uncertainty. For 3 days, the universe reminded them that even the most sophisticated instruments can be blind at the very moment they seek to see. When light returned, 3 iAtlas was already retreating, dim, shrunken, and eerily unchanged in shape. It had passed through the sun's furnace and come out quieter, darker, and somehow more deliberate, as if the heat had not destroyed it, but completed something it had come here to do. When 3 iAtlas finally slipped past Mars and drifted into the inner solar system, attention turned to what the planet itself had endured. To the human eye, nothing seemed different, a red desert wrapped in cold silence. But to those watching through the instruments of MAVEN, ExoMars, and Mars Express, something subtle lingered, a faint residue of interaction that refused to fade. In the first weeks of December 2024, as the comet's magnetic threads collapsed and its plasma tail broke free from the Martian sky, MAVEN's and GIMS spectrometer recorded elevated levels of ionized oxygen, nitrogen, and argon in the upper atmosphere. Normally, those ions recombine and settle within hours, but this time they persisted for days. It was as if the planet's ionosphere had been charged, primed by a passing current that left behind an afterglow. Further analysis revealed trace isotopic shifts in Dunchino divided by Dun-Salto and Dun-N divided by Dun-Salton-N ratios, minute but measurable. The changes were too small to affect the global composition, yet they confirmed an injection of energy high enough to break molecular bonds. Mars's upper atmosphere had briefly become a chemistry lab. Its gases stirred, electrified, and then left to settle back into equilibrium. Down in the thin Martian sky, something else appeared. The Mars Reconnaissance Orbiter, MRO, captured transient faint streaks of luminescence over the southern hemisphere, soft blue-green flashes that flickered for seconds at a time. They weren't lightning or aurorae in the usual sense. They appeared lower, around 60 kilometers altitude, where no such activity had been recorded before. The team at the University of Colorado Boulder called them ion curtains, ghost-like veils formed when charged particles interact with residual dust in the atmosphere. Meanwhile, the Trace Gas Orbiter continued its scheduled methane scans. It found none, but it did register elevated concentrations of carbon monoxide and molecular oxygen, both products of photochemical reactions. Mars had been chemically stirred, but not by sunlight. Something else had introduced enough energy to fracture CO2 and leave fragments behind. The surface, too, bore subtle hints. The Mars Climate Sounder picked up mild temperature anomalies near the equator, circular warm patches about 40 kilometers wide that faded over several sols. The differences were tiny, only a few degrees, but the geometry caught attention. The patterns resembled interference rings, concentric waves of heat spreading outward before dissipating into the cold. ESA's Mars Express attempted radar passes to probe the subsurface. To the scientists' surprise, signal reflections from certain equatorial regions came back weaker than expected, as if the upper soil had temporarily changed conductivity. Some proposed fine dust electrification particles retaining charge from the passing plasma stream. Others suggested the thin film of static electricity might have interacted with trace atmospheric gases, forming short-lived conductive layers. None of these effects were catastrophic. Mars endured as it always has, patient, resilient, unchanged to casual eyes. But to those parsing the data, it felt as though the planet had momentarily awakened. For a brief window, its long-dead magnetic skeleton had flexed, its sky had glowed, and its air had breathed differently. When the reports reached ESA's Planetary Science Archive, the summary was terse. Localized transient ionospheric and photochemical disturbances observed. No lasting planetary alteration, yet many at the agencies disagreed quietly. There were patterns that couldn't be dismissed as coincidence. The alignment of events, the magnetic coupling, the ultraviolet pulse, the lingering ions followed a rhythm too precise to feel random. Mars, it seemed, had responded to 3I Atlas, not with destruction, but with resonance. Months later, when the plasma cleared and Mars returned to its usual quiet, Maven still picked up faint background oscillations, rhythmic fluctuations barely above noise level, repeating every 11 hours, the same period once recorded in the comet's rotational cycle. It was as if a ghostly echo remained, woven into the planet's upper atmosphere, slowly fading but never entirely gone. In the end, 3I Atlas left Mars unbroken but not untouched. It left behind traces of electricity, altered gases, and a memory imprinted in thin air. The planet went still again, but for those who listened closely, Mars seemed to hum softly, almost imperceptibly, as though remembering a brief conversation it once had with something that came from between the stars.